All right, Heidi, you want
Hello.
to kick things off after Balaji introduces us, I guess?
Yeah, I'll get the proceedings started and then pass it over to you.
Great.
Okay, hello everyone. Welcome to the IEEE Region 4 Industry Engagement Committee's webinar series. And today we have a webinar on the topic of VRM modeling and stability analysis for power integrity engineers, presented by three distinguished speakers, starting with Benjamin Dannan of Northrop Grumman, and then Steve Sandler of Picotest Inc., as well as we have Heidi of Keysight Technologies to talk about and share their expertise on this topic. And at any point of time, if you have questions for the speakers, please type that on the chat, and we will address them as we go through the presentation. And with that, I request both all three of them to take over the proceedings, and we look forward to the talk.
Yes, thank you very much for the introductions. I'll go ahead and kick things off. This is the paper that Steve and Ben and I just presented earlier this year at DesignCon, which is one of the premier signal integrity and power integrity conferences in the world. The title of the paper is VRM Modeling and Stability Analysis for the Power Integrity Engineer. And I think, yeah, okay, thank you very much. And the outline, like I just mentioned, we're going to talk a little bit about why do we want to use the Sandler state space average model? Why do we want to use this behavioral model for the voltage regulator in simulations? And then we'll take a closer look. Steve will go into how to populate the Sandler state space average model with design parameters and measurements. And then Ben will actually show us what the process is. He'll actually go through a real world of example of how he learned how to populate the state space average model and run it in simulations and use it to debug some simulation to measurement challenges in terms of building a digital twin that can accurately predict what you measure. And then finally, he'll take a closer look at how this state space average model compares to a lumped SPICE model. And then we'll have a call to action and summary. Next slide. So here, obviously, when you model your power delivery network, the power supply is a major component in the delivery of power to your load. And so it's very important to actually be able to see the DC to DC converter switching noise, make sure that that power supply is stable. And with this Sandler state space average model, it's very easy to get all of this large signal and small signal information all in one simulation and get a lot of great detail all at once. And this model, the state space average model you can see here, is actually working for multi-phase. It works for a single phase all the way up to N phase, and it's easy to use. Next slide. The idea behind the state space average model is that if you think of the VRM as a network, there's the input and the output, and we can think of this in some respects you know, of where all the noise sources are coming from. And so if we model the voltage regulator, we need to consider all possible noise sources. Noise coming from the input, switching noise on the output, and how that couples back and forth between the input and the output. So we care about things like output impedance, we care about reverse transfer, we care about power supply rejection ratio. And the interesting thing is that we start to learn how important impedance is when we start looking at this type of model of the noise parameters. Next slide. The state space average model is simply a behavioral model. State space average techniques are very common both in the mechanical and the electrical world for modeling control loops. And the idea here is just to average out that dynamic switching behavior, because we're pulse width modulating an upper switch and a lower switch to down convert our voltage. And there's two states. One is with the upper switch on. The second state is with the lower switch on. And so we're going to be taking the average of those that behavior. And there's some very simple equations that govern that DC to DC converter topology. And that's sort of the basis of these state space average equations that we'll be using in this model, the Sandler state space average model. Next slide. So before we go too deep into the Sandler model, the other question is, why would we want to invest in this? Why would we want to create a behavioral model? Well, for one, it gets us closer to the real world. And here you can see this chart. If we have the very simplest voltage source is an ideal voltage source. And that obviously doesn't give us the right impedance, and it doesn't give us any of the DC to DC converter switching noise characteristics, any of the noise sources. But if we do an RL model, that's sort of, you see that as a classic example in a lot of signal integrity simulations, just using a simple RL model. Well, it works okay to kind of get the impedance, not real well, but it can get some output, does give you an output impedance over frequency, but it doesn't give you any of the other noise parameters. And even if you try to be more sophisticated with a LR, a little bit more complicated multi-element SPICE model, you can start to match the output impedance of your regulator correctly, but you still don't get any of the other typical characteristics of a regulator noise sources. Whereas even a bad state space average model, just a best guess at the state space average model, will start to give you a lot more information. So with the state space average model, we get the large signal switching ripple, we get power supply rejection transients, the noise going from the output to the input. We can also get control loop stability. There's a lot of information that we can get with a state space average model. So with just a very simple behavioral model, even if it's not the highest fidelity of state space average models, it's still a lot better than your simple SPICE models. Next slide. And how bad can a simple RL model be? Well, if your voltage regulator output impedance is not, say, a resistor, if it's not a flat impedance versus frequency, then it's not going to match that RL model. And if you try to use an RL model, oftentimes it will interact with your decoupling capacitors and create a resonance that really isn't there. And if you look at the measured data here, the measured data is actually in black. You can't really see it because the state space average model is right on top of it. Now, obviously my RL model is not matching. I only have 2 elements and I can't match that shape of the measured curve. But if I add more elements in LR, I can start to match it more closely. But like we mentioned before, you don't get all of those other noise sources. You're just matching the impedance. Whereas the state space average model will dig in and show you how we can build that and be a lot more sophisticated and have a higher fidelity simulation. Next slide. So the nice thing about taking a little bit of time to do some measurements and getting an accurate behavioral model using this state space VRM model is that once you have that, now you can start doing some tolerance analysis. You can start modifying component values. Here you can see some Monte Carlo type sweeps to look at how robust is your design, how sensitive it is to components and process variations. So very useful information that you can start to get with this simple behavioral model. Next slide. And here's where I'm going to turn it over to our expert, because he created the Sandler state space average model. And this is a model that is modeling actually real world power supplies that are actually functional and working and stable. We're making sure how robust they are. We're not really trying to run these power supplies in unstable regions. And so Steve is going to kind of go into a little bit more detail about where this model is accurate and how he's compared it to some of the other methods of modeling power supplies that are out there in the industry. So with that, Steve, I'm going to turn over to the expert. You're the inventor of the Sandler state space average model, and I'll let you talk to this slide here of how your model compares with others in the industry.
Oh, thanks, Heidi. So, this model isn't new. I wrote this model back in the 1980s. So it's probably almost as old as the average dinosaur at this point. But there was a reason that I wrote my own model. There were other state-space average models back then in the 1980s. In fact, there were even state-space average models in the 1970s. There were a lot of disputes about who first did the state-space averaging of power supplies. Dr. Vincent Bello claimed that it was him. Volparian claimed it was him. But there were plenty of models out there. So why did I need to write my own? I needed to write my own because the models were very specific. And so, for example, we did have state-space models that operated in discontinuous conduction mode. And there were state-space average models that operated in continuous conduction mode. There were models for current mode a little bit later. Current mode didn't actually exist yet. And there were models for voltage mode. So why did I need to make my own model? The answer was really simple, actually. You know, picture this simulation that's running and the output current is very low current. So the power supply is sitting there in discontinuous conduction mode, and we do this load step, and all of a sudden it crosses the discontinuous continuous conduction boundary. And what are we supposed to do with that? Are we supposed to say, whoa, stop, wait, we need to switch models here? No, we actually needed to be able to run through it. And so I needed to create a universal model that could do large signal and small signal simulations of continuous and discontinuous conduction mode devices in both voltage and current mode. And of course, nothing's free. And so in this simulation, I wanted to do a comparison to the Ridley model. Ridley did his PhD thesis in 1990, so it was about 5 years after I wrote this model. But I went back and I used the example from his thesis to see how well the model lined up. And you can see that up to about a sixth of the switching frequency, the Sandler state space average model tracks the Ridley thesis very, very well. What we're missing is the intercurrent loop stability. And that actually was the main purpose of Ridley's thesis, was to show why it is that we ended up with a subharmonic oscillation in current mode control. The problem is that intercurrent loop resonance only occurs in continuous conduction mode, not continuous conduction mode. So one of the early decisions that I had to make was whether or not that was important for me. And I decided that it was more important that I was able to replicate all of the other parameters and do so up to about a sixth of switching frequency. So that's what I wanted to make sure that I made clear, is that there is a price to be paid, and the price is that the model is only good to about 1/6 the switching frequency. Next slide. In order to try to figure out how it is that these parameters line up, there's really only a few parameters that need to be entered into the state space average model, and most of them we actually know. You know, simple things like what is the switching frequency and what is the value of the output inductor. Those are all critical. There are two parameters that are much more difficult to get and very frequently unpublished. One is the slope compensation ramp. We generally don't have access to that, and many suppliers don't really want to share the information for what that looks like. But that is one of the parameters we need. And the other parameter we need is the transconductance control, particularly for current mode control. And so we have to derive those in some way other than direct datasheet specific data. He actually did a webinar early on with Johnny Hancock from Keysight when he started doing frequency domain analysis in oscilloscopes. And I chose this particular voltage regulator at the time for that presentation. And I chose it simply because it was one of very few devices that actually showed the slope compensation ramp external to the chip. So we could actually put a scope probe on it and measure it to find out exactly what it was that the slope compensation ramp was. That's not really important for us in the long run, but in the short run, we have to prove that we got the right answer when we do the extractions. And using a device that has access to the ramp that we can also extract indirectly allows us to see immediately whether or not we got that right. And so we use the LM25116 for that. Next slide. How the model works It's actually just a bunch of equations, and I don't know, maybe some people are a little bit put off by the equations. They are a little bit nasty looking. But for the most part, you don't need to worry about these. These equations are embedded in the model. And so even in ADS, the model includes all of these equations. You never really have to see them if you don't want to. I did want to include them for a few reasons. One is that a lot of people do want to see the mathematics of it, and so that they can look at sensitivities and figure out how it is that it actually works. I also wanted to include these equations because it shows all of the different characteristics of the VRM that we can replicate using these equations. And you'll see that we can get the control transfer, we can get reverse transfer, we can get the negative input resistance of the regulator, the power supply rejection ratio. We can even see the excess inductance of the voltage regulator, which is not to be confused with the output filter inductor. This is the closed loop excess inductance and the output resistance. But there's really a more direct reason that I wanted to include these equations. And you'll notice that I highlighted in red the two terms that are generally unpublished that are key to populating the model, RI and VRAMP. And you'll notice that those two terms both appear in every one of these equations. And so if we need to solve for two unknowns, we need to have two equations. And that means we can choose any two of these. I chose output impedance and PSR because those are generally very easy to get. One has the most direct relationship to PSR, to VRAMP, and the other one has the more direct relationship to RI. But in theory, we could use any two measurements we want of the converter in order to solve for these two unknowns, RI and VRAMP. Everything else is in black, and you'll see those we generally do know. Switching frequency, input voltage, output filter inductance, things that are very easy for us to determine. There are some things that we don't always know accurately. For example, the RDS on of the MOSFET. I think Heidi said this earlier, but I'll repeat it here. A really bad state space average model is much better than an RL simplified model. And so if you don't know what the RDS on is, it's okay to guess or make a reasonable estimate. The sensitivity of RDS on is relatively small. And if you know what it is, that's great. If not, you'll still be much better than an RL model if you just put in your best guess. Next slide. I'm going to hand it off to Ben here, and Ben is actually going to show the process of how we create the state space average model.
Thanks, Steve. Okay, let's get right into it. So for today's example, we use the TPS 7H 4003 from Texas Instruments. It's a rad tolerant VRM for LEO geo applications. Just because it's a rad tolerant space gray VRM doesn't mean that this process doesn't apply to any other VRM. It's actually the exact same. This was just the VRM that we chose for this example because we were doing something similar at the time, and it made for a great example for other reasons, which we'll show you here in just a little bit. So as Steve and even Heidi touched on this, there are really two main parameters you need to characterize what we call the plant. And I'll show you a depiction of that in just a second. And those two parameters to characterize what the overall gain of the plant is RI and VRAM. And in this case, to start with measuring or characterizing your RI, all you need to do is measure VComp versus I out. Now, if you don't have access to VComp, or you don't have a VRM that has a VComp output, you can still make a state space average model. This just becomes a bit more of a manual process. So things like PMIX or VRMs similar to that sort of architecture, that's where you have a bit more of a manual tuning process. But for this example, we do have access to VComp, and you can see here we just put a voltage probe at the comp pin, and then we're plotting the voltage at that comp pin, VComp versus I out. And you can see here we can create a curve and a line that fits to that curve, and that slope of that line is our RI term for this VRM, which is 26.6 milliohms. And you can see we even have a very good regression, over 99.9%. And so this is the first term that we need to characterize our VRM. Now, the takeaway here, Steve said, if this is available in the data sheet, which typically it's not, it won't always agree with what's in the data sheet. And we'll talk about that in just a second. So keep that 26.6 milliohms in the back of your mind. Well, actually, what do you know? This example, this VRM actually really makes for a good learning example, because TI was gracious enough to actually give us an equation where we can actually solve for the slope comp. And in fact, they actually specify the RI term, which you can see I'm calling out there in that first box, where 1/40 Siemens is the nominal RI at 25 milliohms for 25 degrees C. And so because we now have a nominal value for our I, and we have this equation that they gave us, which is based on this RIC, which is just a resistor that you set outside the part, which I'm showing you in that simple schematic diagram, you can solve for slope comp, right? And so if we solve for slope comp, which we get is 1.1 amp per microsecond, we multiply that by our RI term, we can solve for our VRAMP, right? I'm sorry, 2.2 amps per 100% duty cycle is what the slope comp per duty cycle is. And so our VRAMP comes out to be 0.055 volts. So that's the number you want to keep in the back of your mind, along with that 25 milliohms and the other terms I told you a second ago, 26.6 milliohms. So now we have the two parameters we need to populate this model, and now we can characterize our plant, right? So you can show the open loop gain here, right? And I say open loop gain, what this means is we've removed the feedback loop. We just want to look at the open loop gain of the plant, which doesn't include the feedback loop, the error amplifier. And the reason for this is because if we think about a feedback loop as part of the PSRR, there's all these other dependencies that we don't want to include, and you're going to see why that's important when we get to the measurements in just a minute. And so you can see here our flat part of our open loop gain is right around minus 33 dB. All right, looks good. So now let's go and actually measure it. If we measure the open loop gain, and this is the setup you'd use, and it's a 3-port measurement where you have a probe at the input side and a probe at the output side. And you can see here we're using some great Picotest probes and a modulator, which is the J2120, and that's modulating the signal onto the input side. And that's how we're able to measure the open loop gain. And we're opening the loop by injecting a voltage at beat comp. So this thing is an open loop. Now, if we were to remove that voltage that we injected at beat comp, it would be closed loop, and you'd get the normal PSRR curve. And this is what we get. The left plot shows you what the open loop gain is, and you can see we're right around minus 21, 22 dB down at our flat part of the curve. And if you recall a second ago, with the datasheet nominal parameters that we calculated, we were at minus 33 dB. So we're actually 11 dB different than what the vendor datasheet provided. However, you're going to see in just a second with these parameters that we are within tolerance of the datasheet spec. And if you want to, you can also look at the phase of this measurement, if that's something that you also need to take a look at to address stability of this gain measurement. And a step further, you can actually look now at the closed loop versus the open loop. And this is why we want to measure the open loop gain to characterize that VRAMP term accurately and ensure that when we tune that VRAMP and RI value accurately for a plant, we're using the right parameters for a plant. You can see here with the open loop gain, it doesn't include that closed loop PSRR feedback that's part of the VRM. Okay, so now we have our measurement that we made it, and you can see where we started, right? That black line here in the curve is where we started with the datasheet nominal parameters that gave us that minus 33 dB open loop gain. And if you take our measurement, which was around minus 22 dB, and now we use that to tune our VRAMP and RI values, in fact, we find through this example that what is really set in this part, in this specific VRM that we use as this example, our VRAMP is actually not 0.055, which is what we calculated before, but it's actually 0.15. And our RI value is actually 23 milliohms instead of what we calculated with the nominal datasheet value of 25 milliohms. So those are the things you want to keep in mind. So now we have a good gain setup, right, for our plant. And now we can add in the feedback loop and the error amplifier as part of our setup. Oh, skip the slide there. And so the last two pieces that you want to make from a measurement perspective are your output impedance, right? Steve and Heidi talked about output impedance, and Steve even talked about what he likes to measure, which is PSRR and output impedance. And output impedance tells us a lot of things about the VRM. By measuring off and on, so the VRM on and off, we get a lot of information about the PDN. Not only do we get the passive and active resonances of the PDN, but you also may not know that we get the actual VRM loop bandwidth. And that's simply calculated by taking the off impedance over the on impedance minus 1. And that now gives you the loop bandwidth of your VRM, and you can plot that. The other thing that I'll add here, when you do a two-port impedance measurement like we're showing you here, is that you do want to measure across an open cap pad, especially if you're using a probe of this nature. This is a great probe. I love this probe. However, you don't know what your error term is going to be that's induced if you're measuring across a cap. So it's recommended to really unpopulate a cap when you do this measurement right on your board. Before we get into any sort of simulation and simulation results, let's talk about why Steve and Heidi love to use ADS and what makes it, as they like to say, so blazingly fast. And the real secret sauce here, and it's really not so much of a secret sauce, is the fact that we're using harmonic balance. And harmonic balance is unique because it's a native Fourier simulator. And what that means is that it's calculating steady state in the frequency domain, and it's able to do an inverse Fourier transform and achieve steady state much faster than any transient time domain simulator ever can, and show those results, which is a huge benefit if you're doing these sort of simulations. For those of you who've done any sort of time domain simulations for power integrity or any sort of spice with VRMs, you know how long it can take to get a long enough waveform in time. And with harmonic balance, this takes seconds or even milliseconds to really get a result. It's really that fast. Okay, so we have our feedback loop set in here. We got a spice model for our inductor. We got our plant parameters for RI and VRAMP. We got our gain settings now for our air amplifier. We have a bulk cap model for all the caps on our PDM, and we're set, right? So let's push the button and hit simulate and look at our results. That looks pretty good. Right, you can see our switch node voltage. We're inputting 5 volts, and you can see it's switching from 5 volts to 0. You can see our output ripple after the inductor. It looks like a reasonable waveform. It's around 6.3, 6.4-ish millivolts. And you can even see our output inductor current with we have a DC load on here that's it's approximately a 10 amp load. And you can see we have an average current right around 10 amps. And if you wanted to, I didn't mention this a second ago, but because we're using harmonic balance, you may be wondering, well, if it's doing the frequency domain content, can you get EMI? And the answer is yes. And you can see we're plotting some of that content here. All that information is available to you with the state space average model in this EDA tool, which we're using as ADS. And you can show that frequency domain content and look at that from an EMI spectrum perspective if you want to. Now, moving over to the top row, second from the left there, or second from the right, you can see our output impedance versus simulation versus measurement. And here we can see we actually have pretty good correlation versus our measurement, so that looks pretty good. And then even now our PSRR is actually fairly well correlated, which shows us that with our feedback loop and the parameters that we added in there, including the gain for our plant, we have a pretty good correlation. It's not perfect, but it's pretty close. And so we're done, right? Everything looks good. Well, let's do one more step. Let's compare the output voltage ripple to measurement, what we simulated to an actual voltage ripple measurement. And when we do that, you can actually see there's a pretty big difference here in the output voltage ripple response. And you can see it's actually about a 1 megahertz period of this additional artifact that's showing up in the output voltage ripple. And I don't know about you, but no designer really wants to see this in their waveform from a voltage ripple perspective. This is not something you're typically trying to design for. So one of the other co-authors of this paper, Christian Yachts at TI, it was on my to-do list to add in the board effect. So as soon as I saw that, that was the very next step that I did. So I reached out to Christian and said, Christian, please give me the board for this. I need to extract it. And that's exactly what I did. I extracted the board effects for the switch node and the Vout node, and I added those into the model as I'm showing you here. Here we have 2 pieces that we're looking at, right? Because the top part is the small signal model and the bottom part is the large signal model. And so I added those pieces in there and hit simulate again, and boom, what do you know? There's that artifact right there in our simulation. that's showing up in our measurement. So we have a pretty decent correlation here. We have an idea of the fact that this is some sort of artifact of the piece that's occurring with the PCB. The question is now, what's causing this? No designer wants to see this. How do we fix it? And so the first thought that I thought to myself is, this is looking at the output node. And so maybe this is the artifact of, or maybe we get a clue by looking at the output impedance. And if we go and look at the output impedance plot, this is the measured plot that we did earlier. You can actually see right there, right around 1 megahertz, indicated by marker M9, we have a little tiny blip there, a little tiny resonance. And so that gives us a clue that this is probably a passive resonance because of where it's occurring in the PDN. And so we can take this a step further and do a power plane excitation and look at where the energy is most excited with a 1 megahertz excitation energy, and start using some logic here to potentially rule out our potential culprit. And looking at this, you can see here there's a little bit of uneven current around those output caps, but I don't think that's really the problem. We definitely can rule out those 330 microfarad caps because those are really too big to cause a resonance of this frequency. And if we go to the other side here, those 0.1 microfarads, those are really too small to be resonating right around 1 megahertz. However, we do have two 22 microfarad caps. And in fact, only one of them is actually installed on the physical hardware that we measured, and only one of them is physically installed on an actual simulated model. And so that could be our potential culprit. And when we pull down the vendor spice model from Murata, you can actually see, looking at the resonance point, what do you know? It's resonating almost right at 1 megahertz. So this looks to be our potential culprit, right? Well, let's see. What happens if we remove this from our simulation? And hey, there you go. We remove that single 22 microfarad cap from our simulation model. That 1 megahertz resonance is gone. Great. So now we can do our last step, and we can tune our model to get a good fit to ensure our measurement and our output impedance, our measurement for our output voltage ripple and our simulated output voltage ripple are dead on. And you can see here, after we remove the output cap, that 22 microfarad output cap, that resonance also disappeared. And so using these equations that we show you here, you can tune the output waveform based on some differences that may be in your model versus what's actually on the hardware that you're measuring. And so in this case, you can see we have a really good fit, pretty much dead on. Even the ringing is lining up almost perfectly. So Heidi talked about this. She talked about and Steve even hit on it even more, all the different noise sources that are part of a VRM and why it's important. And you're probably thinking, okay, great. You talked about, spice models, you talked about the noise sources, but how much do I really care, right? And in fact, Steve, if you hang out with him long enough, he'll tell you that there are actually 5 main noise sources that are part of a VRM. And you get all 5 of those with the state space average model. And as you heard from Heidi and then again from Steve, there are some fidelity challenges that you get depending on the type of spice model you get. And you may think, okay, I'm good with an LR model because I have a pretty good fit. However, you might be thinking, okay, how much better then is the state space average model than the spice model? And so this is really the next question that we wanted to explore as part of this discussion. And this is really where we're going next. And in order to explore that, we had to create a fitted spice model. And to do that, we took the measurement for our output impedance and we created an RL model. And you can see that right there on the right plot. And you can see our fitted spice model is pretty good, right, to the measurement. And we can do a step further and compare that fitted spice model to the output impedance of the state space average model. And again, it looks pretty close. But it's not exact, but it's still very close. And so now what we can do is we can analyze this from a large signal perspective. And that's exactly what we did. We applied a 10 amp, 100 nanosecond step load. And in this case, we're showing the results without the PCB effects. And that's going to be important. And I'll show you why that's important in just a second. But you can see here at that initial step change, where that initial step edge is, we're already seeing a 16, almost 17 millivolt greater step change in the transient voltage with the state space average model than we are with the fitted spice model. And if we pan to the right a bit in time, where you start to see that ringing occurring right there around 50.1 microseconds and further right in time, you start to see a lot more differences in the ringing that you aren't seeing in the amplitude with the states with the fitted spice model. So there's a lot of fidelity and a lot of energy here that we're just not seeing in the voltage response with the spice model that we are capturing with the state space average. Now, keep in mind, we already know our state space average model is right. We showed you a measurement correlation. We know the output ripple is right. We know the output impedance is right. We know we're getting the right response for the PSR. So we know this model is right. And so this is the response we're getting for the fitted spice model. Now let's add in the PCB effects. If you add in the PCB effects, holy cow, you can see a much greater step change in that initial step response of over 106 millivolts. And in fact, when you pan to the right in time, where you start to see that ringing, you start to see a phase change occurring. And now we're seeing a greater change in that ringing of over 48 millivolts. And this is just with the PCB effects. Okay, but you're probably thinking, Ben, you said noise, right? You said energy. So how do I really equate that? Well, because we're doing this in a tool that allows us to do this sort of analysis, we can plot the noise spectrum and look at that with that same step load response. And here we did that. We plotted the noise spectrum with that step load for both of those models. And you can see here, we're seeing a 44 dB difference in the noise spectrum between these two models. And if we think about this from one perspective, 40 dB is 100x. So at 40 dB, there's already 100 times more noise in one model versus the other. And we're at 44. What's that? Over 160? So that's over 160 times more noise that you're getting with a state space average model that you will never get with a great fitted spice model. And so that's important. And we haven't even added in the PCB effects yet. If we add in the PCB effects, we add another 3 dB. So this is very significant. And so really, this is where I like to quote Steve, and he likes to say being right matters. And so this is where you are going to show, if you're trying to do these simulations for design sign-off, if you're going to have the right answer. And this noise with the spice model won't be in your answer at all. So we talked about lots of things. We showed you how to build the model. We showed you, walked you through the process. We even showed you how to troubleshoot it and why you care about using this model versus a typical spice model. What we also want to touch on is NISM and stability. And NISM, for those of you that don't know, is non-invasive stability measurement. You're pretty lucky because the inventor of that is also here on this webinar today, Steve Sandler. And NISM basically is a way of looking at the output impedance. And what Steve did is he figured out mathematically how to basically cut the trace and look at the source and the load and use group delay and assess the change in phase to determine stability. And that's ultimately what he's doing. So if you're wondering if NISM equates to a Bodhi plot, absolutely. All that correlation's been done, and those are things you can look up on Picotest.com or some of the other publications that Steve has done in the history of his career. But you may also remember that I talked about the extracted loop gain, right? Because we're doing off and on output impedance, you can plot the off over on -1 result and do the extracted loop gain for your VRM and get a Bodhi plot too. Or you can manipulate this model and inject a signal into the feedback loop and do a traditional Bodhi plot too, just like those folks who are comfortable with that normally would like to do. That's something that's very easy to do in this tool also. And so Heidi touched on this in the very beginning of her slides. Yes, this works for multi-phase. In fact, this is the 4-phase version of the TPS 7H4003. This is actually a representation of hardware that I have from TI. They have a 4-phase version with 4 parts and then an 8-pack where there's 2 ICs per phase. So it's like also working in hardware. And so this is a representation of that. And so you can see you can do that pretty easily also. Okay, so I'm going to paraphrase a quote from Eric Bogatin about signal integrity engineers. And those of you who know Eric Bogatin, he is also another guru when it comes to signal integrity and power integrity. But I'm going to tweak this quote about signal integrity engineers and make it apply to power integrity engineers. And the paraphrase quote basically goes like this: there are really 2 types of power integrity engineers: those that have power integrity problems and those who will. And what that ultimately leads me to from a point is that there are multiple noise sources in the VRM, and I hit on it earlier, Steve hit on it earlier, there's specifically 5. And using a SPICE model, you won't get any of those noise sources except for the output impedance, and you're missing a ton of fidelity in that model versus you can get all of that even with a state space average model that's even poorly designed. And so this ultimately leads to a delineation or a gap between the power integrity and power electronics space that needs to end. Power electronics designers think, oh, okay, design a VRM, I'm done, but they forget to include the PCB effects, which is a problem because ultimately you need to include those effects to see what your system is doing overall from a holistic perspective. And power integrity folks, we're always thinking about the system and how we're going to overall design something that's going to work from an end application. And if you're really afraid of making this model or you're not really sure where to start, well, guess what? I didn't know how to do this model a year ago. I worked with Steve and Heidi. I picked up Steve's book, which is a great resource. There's plenty of online content. There's other papers that Steve and Heidi have done. And Heidi took the workspace that we started, and Steve likes to say she dials those sort of things up to a level 11, and that's what she did. She took that workspace and made it into an awesome tutorial example for folks to pull down, and it's available to anybody, and you can pull down and learn to do this yourself. So if you're afraid, I challenge you to learn for yourself just like I did. So this leads us to our overall conclusion here, right? And Steve, I will quote him one more time. I said this earlier, being right matters. And to get that right answer, you need to use a state space average model that has all those noise sources included and include the PCB effects, right? The state space average model, the Sandler state space average model is easy to use. It supports multi-modes and it works with EM. And if you want to use a SPICE model, don't, because a poor fidelity state space average model is already significantly better than a good or even perfect RL VRM model. That's all I have. Are there any questions?
Yeah, I have a question on the PCB effects. Could you elaborate a little bit more what would constitute that PCB effect and how it is represented in the simulation environment?
Oh, sure. So we took in an ODB++ for this artwork. Let me just go to a good depiction here. So this board here, right? So this is actual physical PCB. There are Gerbers for it, right? So we exported that from Altium. They designed in Altium. They exported an ODB++. So I pulled that into another EDA tool from Keysight, an EM tool specifically, and I extracted the PCB effects, right? So I extracted 2 nodes specifically, right? Because if we're looking at a VRM, I'll go forward here a bit. Oh, I went too far. Looking at a VRM, there are 2 nodes that we care about, right? You have, in this case, an output inductor, so you have a switch node that you need to care about. So we're talking about this node right here, right? And then you have your Vout node, which includes all your bulk caps and the output of your inductor and everything that touches that Vout node. So you have to extract those 2 pieces. And I picture right there. Here we go. And so those are those extracted blocks, right? Now you don't see the caps in here because this is a hierarchical model. And so if I were to push into this, those caps are inside this block here. Make sense?
Yeah, thanks.
Sure.
And maybe another question on the state space average. Though this is for the VRM model, when you do a post layout simulation for PI, how this could be used on any type of board layout that you're trying to analyze for PI, particularly like DCIR drop kind of analysis?
Yeah, I mean, Heidi, you want me to take that one or you want to take that one?
Yeah, I'm happy to take that one. So the state space average model, obviously it also has to have the DC levels there too. So that's actually one of the ways of troubleshooting the state space average model is looking at the DC levels, running sort of a DCIR drop and checking things there and making sure you have things set up. But yeah, it works both DC and AC. But obviously, the main reason for doing the state space average model is it does provide that dynamic behavior. It has the averaged small signal performance, and then it also outputs the duty cycle to run the large signal switching behavior, and then you're capturing all the noise sources. So yes, DCIR drop is a critical step, and it's usually step one in setting up a simulation and making sure you've got the basic topology correct, and even including the PCB parasitic effects of the DCIR drop. But the main goal of the state space average model is really looking at those dynamic noise sources and the dynamic behavior. And that's where it really shines and the benefit shows up. But yes, you can use it for both DC and AC.
Okay, thanks. So I see a question on the chat. Could you go over how output impedance measurements are made? What is an on and off measurement?
I think that's a classic Steve Sandler question, the on and the off output impedance.
Yeah, it is. So I'll take that one. So, when we turn the power supply off, what we end up seeing is the output impedance. And for a current mode controller, that would essentially just be the output capacitors. When we turn it on, we see the closed loop response. Of course, if we go back to small signal theory tells us that the closed loop response is equal to the open loop response divided by 1 plus t, where t is the loop gain vector. So if we solve that for t, we end up with 1 minus open loop over closed loop is the gain function. Open loop is what it looks like with the power supply off, and closed loop is what it looks like with the power supply on. So if we have those two measurements, we can use those directly to solve for the loop gain t. But in NISM, the non-invasive stability measurement from impedance, it also helps us because there can often be a lot of peaks that show up in the impedance, many of them being high frequency passive resonances. How do we know where it is that we're going to put the cursor for the NISM measurement? We're looking for the closed loop peak. And so here you can see Ben has the marker M1 at the small peak on impedance, and there's a coinciding peak in the group delay. The only way we would know that was the right peak to be looking at would be to look at that compared to the off state. And when we look at the off state and the on state together, you'll see that when stability gets poor, the closed loop response is actually worse than the open loop response, meaning the impedance is higher with the power supply turned on than it is with the power supply turned off. And so having that pair of measurements is really, really powerful.
Good question.
The question that everybody wants to ask, but they're all afraid to, is how much does this model cost? And it is free. So there you go. You don't have to ask that question. I answered it for you.
And this is the only workspace that is available for folks to learn, right? I mean, Steve and Heidi and I think Jack Carroll have another workspace that is available. You guys can just Google this. I mean, I host this paper on my website. I know Steve has it on picotest.com. There's some links to these slides, which we can make available. You can go to the website here, which I think takes you to the Picotest site to pull down the workspace that Heidi has really dialed up to a level 11. It's pretty awesome when she took it from to. So it's really easy to learn from and walk through and learn on your own. Use Steve's book. It's actually a really great reference. There are some gaps in there and just a couple minor things, and that's where I worked with Steve to kind of pull those pieces out with this paper. And I think with this paper and his book, and what Heidi and all of us have done together, it really is a closed loop, pun intended, way of learning.
That's why I love working with you guys. You filled in all the gaps and made it look really good. You made me look smart. One thing that I do talk about a lot in power integrity, and I should mention it here, and I know it was in the slides also, is that right now there's kind of a hard dividing line with power electronics on one side of the line and power integrity on the other. And it's really important that we make that line go away and at least blur it. One of the things that Ben showed today is that His ripple was greatly impacted by the layout of the printed circuit board and the locations of the decoupling capacitors. And so as hard as we work to simulate and model our power supplies off the printed circuit board, it's not going to act like that at all once it gets put into a system. And so ultimately, these models should all be used to be populating a system level model so that it works for PE on the left side of the line and PI on the right side of the line, and that we start to blur that. That's really critical.
And I'll add to the folks that may be wondering, well, if you're working on a design, maybe like an ASIC or an FPGA, can this model be used with that, right? You look at legacy Xilinx, now AMD, they give you the PDN kits. I work on ASICs with what I do at my company, and we design our own ASICs, and we do use other folks' FPGAs as well. And we can generate loads for ASIC using CPM models and attach this VRM model to our PDN, and now have an end-to-end model for our PDN to use for design sign-off in the time domain, which is what we do. And so with harmonic balance, we're able to do that much faster, especially with the density and size of these power integrity and PDN models today, right? These models can get very large, especially for some of these core rails. So having this sort of horsepower and way of working through these problems in a very fast and streamlined manner is very important.
Yeah. One last thing I want to cover is that Arif asked if we could go over how the output impedance measurements are made for on and off. And I think I explained the on and off, but I don't think I explained how they're made. The traditional measurement for these low voltage core power rails is called a two-port shunt through measurement. And if you go on the Picotest website under the solutions page, there's a lot of stuff measuring PDN impedance. But essentially, it's an AC Kelvin measurement. And here you can see Ben showing the probe that he used to make the measurements. It's one of our two-port probes. And so this probe actually has 4 tips on it, 2 grounds, 2 signals, and we're doing a force and sense measurement using a vector network analyzer. And so the vector network analyzer sends one signal through one pair of probes, receives the signal through the other set of probes, and the vector network analyzer does the transformation between the S parameters and the impedance. And one beauty of this measurement is that it will work with power off and power on, meaning it doesn't need any supply voltage to work. But also, since it's an S parameter based measurement, it offers really great calibration capabilities that allow us to measure very low impedances and also up to very high frequencies. And so all of that is supported pretty well. So I hope I answered your question better this time.
And Steve, there was one extra question there for the high power. Does it apply to high power switch?
Yeah, I'm not really sure how to answer that because I've never gone over 100 megawatts with it. For the first tens of megawatts, I guess it's pretty much transparent. And I guess for the second couple 100 megawatts, it's also transparent. The answer is it's really not power dependent at all. In fact, I used the same model for the International Space Station for the bidirectional controllers, which are, up around 10 kilowatts or so. It's just a really good model of the plant functions. And so long as we can get the models, accurately, you'll get an accurate representation. I think that there's 2 things that are really important to remember. One is that a bad state space average model is better than not having a state space average model. So I wouldn't worry too much about it being perfect. I would worry about it being good. Another thing about high power is that it's not so much the power supply that becomes important, but the interconnects do become more obvious. Cables are longer and the cables have higher inductance than they do at low frequencies, low power measurements. And so we need to be much more aware of the impact of the interconnects in the model. And so we need to make sure we get those right also. I also see a question about how long it takes to put together these simulations for a typical system. And I think I'm going to let Ben answer that because, Ben actually went through the process. Remember, I made the model, so for me, it's pretty quick. But I think even for Ben, it was probably pretty quick. But Ben, you give me your thoughts.
Yeah, it takes really, there's always a learning curve with everything, right? So once you go through the process once, you realize, wow, this is really quite quick. And For a model like this, to be honest, you can have a model running in less than a half a day. With no measurements using the datasheet parameters, you could have a model running in an hour. Using datasheet parameters like we showed you for this example. If you want to make the measurements, if you're somewhat proficient like myself and Steve and Heidi, you can really make all these measurements in less than an hour or two. It's just really the time it takes for you to set up and make these measurements, pull those into your simulator like ADS, and then do all the tuning from there. So really a day to really build a complete model. That's not including all the output capacitors, but that's just to build the VRM model and assuming you have like a SPICE model for the inductor. So it's really not that cumbersome. And so for folks who are thinking about reuse, maybe agility or efficiency, I built, where I work, where we have a group, we built a library. So we built this model, now we have it in a library, and now we have reuse. So it's not like we're doing it over and over. And when we pull this model into our PDN, if maybe the output voltage is a little different, we just tweak the feedback loop and the output resistors and the control loop as needed to match our design parameters, right? So on the fly, we're adjusting the stability and the control loop to meet what we need from our each application perspective. And it's very simple at that point, right? Because for those who are legacy SPICE folks, you can do all that also in SPICE, but you're missing all the fidelity. And so we get all that fidelity now in a tool like ADS with the board effects, and we can tune it to be more realistic of what the real world actually is, because SPICE doesn't include all the real world effects, right? And so that's where the rubber meets the road. Hopefully that answers the question, whoever asked the question. A good question.
One more question. Are there plans to expand this model into other areas to
Other
include?
architectures like Buck Boost or Buck Boost? That's a Steve question.
Yeah, I don't know. I don't know if I feel like going back to that. What I will say is that I did two of these models. I did the forward topologies and I did the flyback topologies. Could we do a boost? Of course we could. You would just have to get me interested enough to write the equations. Or once you understand the equations, it's not that hard. You could write them yourself. In my book, SMPS Simulation, I actually did derive both models, the model for the flyback and the model for the forward converter. And so the actual mathematical derivations are there, and using that, you could probably create that model yourself pretty simply. If you look back at the equations, and if you're in ADS, you can actually see the equations, just click on the model and they're all there. It's really just time variant points. Remember that, switching power supply is really about as basic as things get. And the entire performance of the power supply is defined by only 2 points. A lot like an oscilloscope, it doesn't actually measure lines, it measures dots. And then, the dots all get connected by software, curve fitting. In a power supply, it's not all that different, only the curve fitting is a little bit simpler. There are 2 exact points we know. We know the point that a cycle starts because that's the switching frequency. And so we know the clock comes along and it sets a pulse to start. And then there's a point at which the cycle is terminated. If in a current mode controller, it means that the current reached the threshold. In a voltage mode converter, it means the ramp reached a threshold, and that terminates the cycle. Everything in between those 2 points is just emulated as a linear ramp. And so we just connect the dots. And in every topology, we could do the same thing. What gets more difficult about the flyback and the boost and some of the other topologies is they have right half plane zeros. And you'll see in my switch mode power supply book, I also talked about that and said that, because the right half plane zero only occurs at some operating points in some operating modes, it's not included in my model. And so you need to be aware of where the right half plane zeros are just to make sure those don't get you in trouble. But in the forward model, it's very similar. We're not showing the inner current loop, and that doesn't mean that we shouldn't assess the inner current loop. It means that my model won't represent that half frequency subharmonic oscillation. And to be honest with you, we actually do use Ridley's model, or there are a lot of better newer models for it now also, and we use those only for the purposes of evaluating the intercurrent loop stability.
Okay, thanks a lot.
Sure.
So if there are no more questions from the attendees, then thank you very much, Heidi, Ben, and Steve for excellent talk and insight into new techniques for doing power integrity. Great learning opportunity for all of us, and we can start using the state space model over the others. And the recordings for link would be posted and sent to everybody. And once again, thanks everyone for joining this webinar this evening. Have a great rest of the day.
And thank you for the opportunity. Thank you.
Yeah, thank you.
Thanks. Thank you, everyone.
Thanks. Bye-bye.